my name is Shreyas, and I'm a 0th year grad student at Caltech. I'll be starting there in the fall. I did most of this stuff at Columbia. And like Brendan said, I'm going to be talking about predicting complex organic molecule emission from the TW Hydra protoplanetary disk, which is this Eye of Sauron-like thing in the center of the slide. So that's a lot, and I'm going to try to break this project down into little pieces so that hopefully you can take something away from it. Starting with this. Room full of astrochemists, or astrobiologists rather. Why do you all care about what a protoplanetary disk is? Well, I wrote this talk before realizing that everyone was going to talk about this, so bear with me while I go through the introduction again. But I'm going to try to pay a little bit more attention to why they might be astrobiologically significant. So as astrobiologists, we are in some way or another all interested in life in the universe, right? As we know it, it's a planetary phenomenon. We obviously know about life on Earth. We heard a great talk yesterday about habitable zones and biosignatures in exoplanetary systems. So our mindset is sort of a planetary one. And that brings to light an interesting question. Is there anything inherent within the process of how these planets form that seeds these planetary systems with the materials necessary for life? And by materials necessary for life, I mean complex organic molecules, as has been talked about at length by everyone else. So that kind of behooves us to look at the process of how stars and planets form and see if there are any interesting chemical environments that we can investigate. So yeah, you've seen this picture before. You start off with a large, cold cloud of gas and dust in the interstellar medium. Parts of this cloud can become overdense and get denser and denser and hotter as they accrete more material, thus forming a baby star or a protostar. But this process isn't rotationally static. The accreting material has angular momentum, and so to conserve it, what ends up forming around the protostar is a disk of that same gas and dust called the protoplanetary disk. And it's so called because the material in that disk is what ultimately ends up being the stuff that forms planetary systems. So in some way, you can kind of think about the protoplanetary disk as setting the chemical inventory for the material available in this forming planetary system, which makes it really interesting and important to study. So let's do that. Before I jump into explaining this cartoon of a disk, I want to reiterate something that's been talked at length before. There's kind of two ways we can think about forming complex organic molecules. One way is in the gas phase, wherein you have two-body gas phase collisions. Or another way is on icy grained surfaces, right? Keep that in mind. And as was mentioned twice before, I think, we can't really detect complex organics in the ice phase unless the source is backlit. So we really can only detect things in the gas phase. So with that in mind, let's look at the different parts of this disk and see where the complex organic species might be residing. So in this sort of red region up here, the disk atmosphere is kind of hot, so there's not a lot of gas phase chemistry, or not a lot of ice phase chemistry happening. And there's a lot of radiation, so even if complex organics do form, they're oftentimes broken up by radiation into radicals, ions, other constituent species. So no dice there, right? So in this blue region, the disk midplane, it is cold. So you do have the ability to make complex organics on ices. But in this cartoon scenario, sometimes there's not enough radiation that comes in and pops those things off of the ices for us to observe. So this is kind of like, in this situation, a Goldilocks thing, right? It's up here, it's too hot. Down here, it's too cold. So somewhere in the middle, in this yellow region, there's just the right amount of heat and radiation to have these molecules form in the ices, but come off into the gas phase for us to observe. That's what's called the molecular layer of the disk. And that's where we expect to find molecules like methanol, CH3OH, and methyl cyanide, CH3CN. Now, I keep saying observation of these molecules. I want to take a second and talk about how that actually works. I'm not a radio astronomer, but I'll just go through it quickly. How these molecules emit light, which are then observed by us here on Earth. So in this obviously cartoon situation, imagine a methanol molecule floating out in space. We know the rotation of molecules is quantized. It can be excited to a higher rotational state, maybe by collision with H2 or something. It can relax to a lower rotational state, but only if it's accompanied by the release of a photon at a very specific wavelength. And of course, if that wavelength is in the millimeter or submillimeter regime, it can be picked up by ALMA. Well, not one specific photon, but you can imagine if this is an astronomical source, you can get enough photons to produce an observable signal. So that's kind of how that works. But as I said before, this kind of rotational spectroscopy only works for molecules in the gas phase, right? And I mentioned how a lot of these molecules are thought to form on ices. So let's briefly lay out how that happens for one example. So this is kind of a picture of how methanol forms. Basically, you start off with the carbon monoxide ice, and you keep hydrogenating it on the surface until you end up with methanol. The different directions of arrows suggest that this is not as simple a process as that, but for now we can treat it as it is. But even then, you get methanol on ice, right? So how do we get it off? One way is thermal desorption. If it's hot enough, the methanol can just come off on its own. Another way is photodesorption, wherein you have an energetic photon that pops it off that way. There's also reactive desorption, which I won't get too much into. But basically, yeah, this is kind of the status quo, right? We feel like we have a good idea of how some of these complex organics are forming, how they come off the grains, how they emit light. So putting that all together, if we have all of these components, we should be able to build some kind of predictive model for how chemistry occurs in these protoplanetary disks. And that's sort of what I was tasked with doing, is trying to build such a model for one specific protoplanetary disk, namely the one around the protostar TW Hydra. So let me talk about how I built that model. We started off with a physical structure that's sort of been pre-calculated by another group. If you're interested in who did that stuff, come make friends with me later. But what you're looking at is a radial slice of the disk. So radius on the x-axis, height on the y, and the color scale represents the gas temperature. So parameters like gas temperature, dust temperature, density, ionization field, all sorts of stuff have basically been pre-calculated for us on this cylindrically symmetric grid. And to this grid, we hook on a chemical model. And if you're unfamiliar with how rate equation-based chemical modeling works, let me briefly walk you through that, because I'm sure some people don't know what it is. So you have a chemical reaction, x plus y equals z. You can write down the rate for that reaction as sort of an ordinary differential equation. So the rate at which z is formed is proportional to the concentrations of the reactants times some kind of rate coefficient. So people much smarter than I have compiled enormous databases of reactions like these in the gas phase and on ices that occur in these sources. And so you can imagine that's a 9,400 equation-strong system of coupled ODEs, so you need a computer to solve that. And once you do, you get something called the chemical evolution as a function of time. So in this case, you could get the concentration of z as a function of time. So you pick a suitable time to stop at, and we do that at each grid point throughout the disk. And doing so allows us to kind of see the chemical structure of the disk on a large scale. So what does that look like in practice? I'm sure people don't really care about the methodology. So in practice, this is what it looks like for methanol. Again, you're looking at a radial slice of a disk, so radius on the x, height on the y, and the color scale is the number density of methanol. And I've sort of labeled the kind of different phases in which you can form gas phase methanol and sort of the precursors to the gas phase methanol in parentheses. So what do we see here? We see sort of a small but significant hot gas reservoir in the upper disk atmosphere, but most of the methanol seems to be coming, that same thing that I was talking about with things being formed on ice and photodesorbing or reactively desorbing off of the ice into the gas phase for us to observe. So great, it seems like things kind of stack up the way we thought they would, right? So the next step is taking the output from this chemical model and running it through a radiative transfer code, which I definitely don't have time to talk about in detail, but you can think of it as a black body that turns the chemical model into a synthetic observation comparable to real ALMA data. So that's what we did. My advisor was involved in observations of methanol in this source last year, so she gave me data for that, and I compared that with my stuff. So what you're looking at is the disk, which is actually oriented close to face on towards us, RA and DEC on the x and y axes, so you're looking at position on the sky. Don't worry about the color scale, that's the velocity structure of the disk. But the black contours are my synthetic observations, and the green contours are effectively the real observations that were carried out. So you might be looking at this image and thinking, for all this talk about this fancy astrochemical model that you made, it seems to do a pretty bad job. And you're right. So, so let's try to figure out what's going on here, right? The first thing you might notice is that the sort of green contours aren't really super symmetric about the origin of the disk. And according to my advisor, who is a radio astronomer, not me, who is not, this is due to low signal-to-noise ratio in the observations. So that's not something I can directly fix. Another thing you might notice is that the black contours are really extended relative to the green contours. And I'll talk about that in a second. And the third thing, which you definitely couldn't have noticed because I had to artificially inflate this so that the plot would even show up, is that the black contours are actually really weak. They're about 5 times weaker than the observations, which Ryan Loomis pointed out yesterday are already pretty weak to begin with. So what this means, in essence, is that there's something missing from the model that should be producing a more compact, more abundant reservoir of methanol than we're seeing. And we've been looking into mechanisms to try and figure out why this might be happening. If I have time, I'll talk about it at the end. If not, come make friends with me at lunch. But for right now, this is kind of the status quo. But we can play the same game for other complex organics, right? So we did the same thing for methyl cyanide. Same physical structure, same chemical model, et cetera. And this is what the chemical model output looks like for methyl cyanide. And you can see it's like kind of markedly different than the methanol story, right? Whereas with methanol, we had a lot of stuff forming on ices and photodesorbing or reactively desorbing off of the ices. With methyl cyanide, you see that there's a lot of methyl cyanide gas up here in the disk atmosphere. So there's a lot of methyl cyanide forming in the gas phase. And this is kind of at odds with that whole working hypothesis we had before, that observations of these complex organics are tracing the molecular layer and the disk ice structure. Because in this case, because methyl cyanide has increased gas phase pathways to formation, it might, according to our model, it might be tracing the disk atmosphere more so than the cold gas in the disk molecular layer. So the next step from here would be to compare these to observations, but unfortunately we don't have any published observations of methyl cyanide in the source yet. But we also did some feasibility studies to see if we could do that with ALMA in the next cycle. If you're interested in talking to me about that later, come find me. I also have extra slides for that too if I have time. But for now, I just kind of want to go back and give a summary of what we talked about. So first of all, we talked about how protoplanetary disks are important environments because they can set the chemical inventory for forming planetary systems. We then talked about how complex organic molecules can trace disk ices in the disk molecular layer, but then we sort of challenged that by showing the example of methyl cyanide, which might actually be tracing the disk atmosphere due to its increased gas phase pathway to formation. That's a mouthful. And finally, we showed that even when we do think complex organics should be tracing the disk ices, there's an enormous discrepancy between what our modeling and what theory says should happen and what the observations actually show, which is as of yet unresolved. So clearly, there's a lot of work left to be done. I have a little bit of extra time, actually, so I'll talk a little bit about what we're looking at for reasons that this discrepancy might exist. So what are ways in which we can produce compact, abundant methanol? One way that we've been considering is called co-desorption, in which this methanol is forming on carbon monoxide ices. Sometimes the carbon monoxide the methanol can get caught up in the carbon monoxide, and thus when the carbon monoxide desorbs, it can carry off a little bit of methanol, which is more volatile on these surfaces. And so we thought that this might give sort of a boost near the carbon monoxide snowline. Unfortunately, we've gotten laboratory results back about this process, and it doesn't look like it's actually a thing. So that's one way we were looking at. There's other stuff too, but I think I'm running out of time, so I will stop there. Thank you.
Hey, really nice talk. So you said in your model you're running the chemical model for every individual cell in your model disk. Is there any crosstalk between the cells, like turbulent mixing or transport or any of that?
Yeah, that's a good question. No, there's not.
Okay. And how do you think that would affect the results?
So yeah, there's the turbulent mixing thing. One thing that we were thinking it might do is there's the vertical turbulent settling in which a lot of these species drift inwards towards the midplane. So that might be one way in which there's also like the inward radial drift of the dust grains to consider. That's actually one of the other things we're considering is radial drift, but we haven't done it yet, I should say. So stay tuned.
Great talk. If you go back to the plots of the methanol abundance, you plot that as absolute abundance. Is that both gas phase and ice surface?
No, it's just gas phase.
It's just gas phase. Okay.
Yeah.
So then the hot component up there, what is the pathway that's producing that? Because methanol can only form through grain surface processes, right? So is that just through transient adsorption and desorption off of grain surfaces up there, or?
Yeah, it's a lot of that, and there's a lot of like, so when we were looking at this, there were a lot of other gas phase processes that honestly look kind of sus, and it's because I don't think the chemical network is super complete at high temperatures, the high temperatures that are sort of in that kind of region. So.
Okay, great.
Yeah.
Astrochemists aren't scary, I promise. All right, I got one. So how representative is, say, the hot core phase after you run it through the protoplanetary disk phase? How much, like if I knew the abundance in a hot core phase and then I ran it through a disk, how badly does the disk scramble the chemistry?
That is a really good question, for which I don't have a really good answer. I think there's evidence that it does scramble the chemistry some, but not all. I think there are people that have shown that a lot of water is inherited directly from like the cloud, the initial cloud. What we assume for our initial conditions here is we take a dark cloud model, run it to an appropriate time, and then assume that the disk inherits its ices from the dark cloud model, which is obviously not the most accurate thing to do, but if you have a better solution, please let me know.
Okay, any more questions? Then let's thank the speaker again.